Right, so thank you for introduction. First, I'll start by covering some basics about the clustering and more specifically soft clustering with Gaussian mixture models, and then I will move to federated setup. So roughly speaking, we can divide the clustering methods into the hard clustering methods and soft clustering methods. For the hard clustering methods, the data point can belong only to one of the clusters. And then with the soft clustering methods, the data point belongs to multiple clusters with the varying degree of membership or varying, for example, probability. So one of the example of hard clustering method been discussed a few weeks ago, it's a k-means clustering, and each cluster is characterized by the centroid. Now, when it comes to the soft clustering and specifically to Gaussian mixture model, the main idea is that we assume the data can be divided into several subgroups. For example, in this sketch illustration, we have three subgroups of the data points, which are more similar to each other. And our assumption is that we can fit or find such a Gaussian distribution that will describe each of the cluster well. So for each of the cluster, we have to find some Gaussian distribution with a certain mean and variance. And then using these parameters of the Gaussian, we can actually compute what is the probability that the data point belongs to one of the clusters. That's how we are obtaining our so-called soft labels. So to make it a little bit more concrete, let's look at this illustration. It's very simple data set, it's like just a synthetic data set. It's a 1D, and let's assume that those are, for example, height measurements of some population of people. So we can see here that roughly, even visually, we can divide this data set into two groups. So we assume we have like, for example, two clusters in this data. And we can guess, for example, that these measurements maybe they are coming from one generation, data generation process. For example, this data may be coming from the measurements of the female height, which are on average a little bit shorter. And this, for example, could be measurements from a male population, which are on average a little bit higher. So in a more abstract way, we can say that these data points are coming from two different data generation processes. So what we want to achieve with the Gaussian mixture model is we want to find such a Gaussian distribution. Each Gaussian distribution is characterized by mean and variance that will feed these two data generation process very well. So, and having these parameters of Gaussians, then we can build a probabilistic model, which is characterized by this formulation here. So it's a probability density function for a data point X, which is a weighted combination of the each of the Gaussians. For example, in this case, we have two Gaussians. So in addition to the mean and variance, we can see here that there is this coefficient that we used when we are computing this weighted sum. This is pi k for each component, for each Gaussian, and it's called mixing coefficient. And roughly speaking, it just quantifies the impact or contribution of each Gaussian to the total distribution. For example, here we can see there are more data points which are of this orange color than this blue one. So we can expect this pi k gonna be larger for this Gaussian than for this Gaussian. It's just like a proportion for both of the distributions. And then the ultimate goal of such model is to find such parameters, the mixing coefficients, the mean vector, and the covariant matrices or variance that will give us the highest likelihood of the given observed data given these parameters. So this is a kind of a loss function that we're optimizing in the end. So the question is how we are coming from this to this, because obviously we don't know from which data generation process each data point comes from. If we would know that, that would be very trivial to compute, right? So we somehow start to discover these Gaussians with its parameters. And the most traditional or most usual way to find these Gaussians is expectation maximization algorithm. It's an iterative algorithm, and in its spirit, it's very similar to K-means algorithm, but with a probabilistic twist, let's say. We also start with the initializing the parameters, and then we repeat two steps until some criteria is met. We have E step, expectation step, and M step, maximization step. So in the E step, in the first step, we compute membership probabilities for each data point given our initialized parameters. And then on the next step, we update these parameters using these computed probabilities. And then we repeat this with the multiple steps. I'm not going to go into detail of the EM algorithm because it involves some amount of formulas, and I'm not sure if I have a time to go through them today. But if you are interested, you can check the classic Bishop's book, Pattern Recognition, and it's chapter 9. So there you can find all the formulas and all of the details, how it's performed in practice. Any questions at this point? No, okay, then I'll move. Okay, let's move to federated setting. So in the federated setting, we have a number. Oh, sorry, there's something. Okay, so
sharing the book.
Yeah, it's a link to the book. Thank you. So in the federated setting, we have number or collection of clients, of users, of nodes. It could be a phone, it could be some wearable devices that measure your physical activity or whatever, or sensor network. And each of these nodes performing this clustering task locally. And we want somehow connect these all devices and perform the clustering collaboratively. But the main problem that we usually don't want to share the raw data due to the privacy reasons or due to some computational constraints. Maybe it's not feasible to share the raw data via our communication channels. So we have to find a way to train or to do the clustering on all of the nodes collaboratively, but without the sharing raw data. And more specifically, I'm interested in very specific setting. I'm interested in cases where the data sets on each of the local nodes are very different, so-called heterogeneous local data sets. The case where local sample sizes are small and we have a high dimensionality data. And one big assumption that we have here is that this similarity graph, the similarity between local data sets on each node is given to us, is available. And I'm not addressing the question of like how we can actually get it. It just assumed to be given. And now here I'm presenting the algorithm itself. I call it graph-fed EM because it's graph-based, it's federated, and it's based on the EM algorithm. It's very simple algorithm. Basically, what we have a local EM updates where we learn the parameter for these Gaussians, for the components, independently on each node. And then we can share these parameters with our neighbors. And the neighbors are the nodes that have similar data distribution as other connected nodes. And where we have these shared parameters, then we perform the aggregation of the parameters. And this aggregation described by this formula here. And loosely speaking, it just the averaging of all the parameters learned locally on all connected nodes and weighted by certain weight. So we have this Aij, which is a weight on each edge connecting to different nodes. And also we have this Nk, which basically reflects the effective sample size for which each component, each Gaussian is responsible for. And then we just normalize it by the total weight. It's some kind of a weighted average of all locally optimal parameters. And the next step, we have a blending step where we have a convex sum of the locally optimal parameter plus this computed aggregated parameter. And this is a way just to control how much this aggregated parameter actually impacts our update. It's mostly based on the trying out. It's like an experimental approach. It's not really based on it's not derived from some principles or theory. It's more like a basic heuristics. So now I'm moving to numerical experiments. And first I'll try very simple setup where I generate synthetic data. It's basically a mixture of Gaussian with a certain transformations. There is a shear transformation, there is a rotation transformation. And the data set on each node is similar. So all of the nodes are similar to each other. There is some variation, but overall they are similar. And then this is experimental results. So I use as a metric log likelihood, which we discussed before, the likelihood of the observed data given certain parameters. And then we have this another matrix, which is called NMI, which is normalized mutual information. So this matrix is quantifies how well our cluster assignments are aligned with the true cluster assignments, because this is a synthetic data. So I know for sure from which Gaussian each data point is generated. So I know true cluster labels for each data point. So then I can compute this metrics which compares the predicted cluster assignments and the true cluster assignments, right? So we have two metrics here. Then I have different number of data points for the local data set. Here we have very small data set. We have only 10 data points per node. Then we have 30 data points per node and 50 data points per node. So this is a relatively small sample size. And then we have different dimensionality of the data. I have, for example, dimensionality 2, 5, 10, 15, 20. As you can see, I'm testing out very extreme conditions because that's what I'm interested in, where the sample size is very small and the dimensionality is very high. If you have a 10 data points and your dimensionality 20, obviously it's very suboptimal condition to learn anything. So when we are looking at the log likelihood, I would say that approximately all the, sorry, I have to first introduce the algorithms that I'm used for comparison. So I have my algorithm here, GraphFed-EM. Then we have centralized training, which is basically when we combine all the data from all of the local node and we fit GMM locally, the mixture model locally. Then we have a local training where we train GMM only with the small local data set. And we have, for benchmarking, another federated algorithm, which is basically distributed EM based on gradient updates. And this algorithm is supposed to also handle heterogeneity of the local data sets well. So we have these three kind of a benchmark algorithms and our algorithm. So when we are looking at the log likelihood, I would say that the differences are not very dramatic between the algorithms. Of course, the centralized model performs better than the others, which is expected. We also can see this gradient-based distributed EM algorithms not handling very well high dimensionality of the data, probably because it wasn't designed to work in these conditions. But when we're looking at the quality of the cluster assignments, we can see some mild differences. So we see that the centralized algorithm works the best, again, expected. And then our algorithm is somewhere between the local training and the centralized training. And it's mostly beneficial when we have this very small sample size on the node. And this advantage is somewhat decreasing when we have enough data points on the node, so the local GMM is performing relatively well. So this is very simple condition where the data sets on the nodes are very similar. Now we're moving to different setup, so-called label skew, where we split the data a little bit differently. So in this case, the data on each node can be different. As we can see here, we want to learn three components, but each node has access only predominantly to some of the components. So this node has access to the data points from this green component and the blue component, but there's a few data points from the orange one. And the situation is different for this third node. So now it is expected if you try to learn three components on this node, that will fail because you just don't have enough data points to actually learn this component. So, and when we check the numerical results, we actually see what we expect to see, that the local training is actually performing quite bad because obviously there is not enough data points to learn it properly. And the best one is centralized training. This one is, I think it's just some outlier due to some maybe unfortunate gradient updates. So maybe I'll just need to filter it out. But in general, again, when we're looking at the log likelihood, the difference is not very dramatic between the different algorithms. But when we are looking at the cluster assignments, we can see that here is quite a big difference, especially when the sample size on the local dataset is very small. And we again see that this distributed EM algorithm for some reason suffering quite a lot. Maybe it's a suboptimal condition for this algorithm, but our algorithm performing quite well. And again, when we are increasing the sample size locally, these advantages somewhat diminishes, but still. Now, another setup, even more complicated situation. So here we have a so-called cluster GMM. So basically what I do here, I generate several different GMMs. For example, here we have mixture model 1, mixture model 2, mixture model 3, and each of this mixture model has its own three components. And then the local data sets generated in such way that they belong to either of these mixture models. And then edges are mostly placed between the nodes coming from the same GMM. Let's say these orange nodes, they are well connected between each other, and they are all coming from this mixture model 1, and this blue one, they are also connected more between each other, and they are coming all from this mixture model 2. But there is a few connections between local data sets coming from different GMMs. So this is a kind of a cluster, what I call cluster GMM. And again, if we think about this setup, of course, it depends on the data geometry, how much these GMMs are overlap, or how much these components overlap, what is the separability between them. But in generally, training, for example, a centralized model on this setup, maybe it's not very smart idea because those are three different mixture models. And as expected, when we check the results for this experiment, here I have three clusters, three different mixture models, and I draw 5 local data sets for each mixture model. So this is idealistic setup. I only connect the nodes which are coming from the same mixture model, and there are no out of the cluster connections. We can see here that the centralized training is failing quite badly, which is again expected. And this new algorithm here in red, it's Oracle. Basically, the Oracle is just our algorithm which knows it's actually it's Oracle pool. It's just GMM fitted for each of these mixture models separately. So this is kind of a upper bound on the performance of all this algorithm. And then we can see that training locally is somewhat below our algorithm, but better than centralized. So again, as expected. And again, this kind of advantage of our algorithm is diminishing once we go to the more higher number of data points locally. And again, surprisingly, this distributed EM algorithms is underperforming, but this improves with the increased local sample size. So I just assume maybe there are some hyperparameters that might be adjusted to fit better this local small sample size locally, but this maybe I need to try out a little bit more. Okay, any questions at this point? Because there are more graphs coming, so. All right, no questions. Okay, so I'm moving to very similar experiments, but using somewhat realistic, well, kind of semi-realistic data set. It's a MNIST data set. It's a handwritten digits, images, 28 by 28 pixels. And of course, that is a little bit too much features. So I use first dimensionality reduction to a certain lower subspace. For example, here we have these images projected to 2D space with using UMAP dimensionality reduction. As you note here, we have different blobs with different colors, and each of these colored blob corresponds to separate digit. So as we can see here, these data sets is very nicely can be transformed to a data set which can be used for like clustering problems because it separates quite well. And again, I'm using the similar approach. First, I test what happens if we split this data more or less approximately similarly between the nodes. And in this case, the way how we split the data is controlled by this hyperparameter alpha. So the higher alpha, the more similar the local data sets. For example, here, it's like kind of schematic illustrations. We have a client ID and we have digits. And the size of this ball is corresponding to number of data points belonging to a certain digits. So we can see here that the way the data is split is very, if we can say, approximately IID. So, and then adjacency matrix is also built in a way that takes into account how this number of data points for a digit similarly split between different nodes. Because these nodes are very similar, we can see that this adjacency matrix is very kind of uniform. So it's a sort of equivalent of a fully connected graph. And then if we change this hyperparameter, we are changing how the data split, and we're introducing once again the label skew. In this illustration, we again see this is a client ID. For example, this client number 1 have a lot of data points of the digit 0 and a lot of data points with the digit 1, but very few of the others. While this client number 0 has more or less samples for each digit. So we can see that here the split is very skewed, and this is reflects in the adjacency matrix. We can see that some nodes are more similar to each other based on how similar this data is split between the nodes. Okay. So again, if we look at the results, here we have this alpha parameter, which controls how the data split. So the lower alpha corresponds to the high label skew, and the high alpha corresponds to the low label skew, or more kind of IID condition. We can see that the local training has very kind of unfortunate log likelihood plot. It's not performing very well when it comes to computing the likelihood. But when we look at this cluster assignment metrics, we can see that the best one is centralized training, again, as expected. And the local training is performing somewhat okayish. And our algorithm is somewhere in between for the high level skew. And again, this advantage is kind of disappears once the split of the data is more or less equivalent. So I have a questions here. Do you also track the loss over time, number of iteration for plots we have seen? So I have fixed number of iterations, and I checked how the number of iteration affects the performance. But what I noticed for these algorithms is that they are settling to a certain solution very fast. That's concerns, for example, my algorithm, which is based on the closed EM solutions. This gradient-based EM somewhat more depends on the number of iterations. So I was actually trying to find the number of iterations that would be optimal for this algorithm. Because for my algorithm, even like a 5 iterations would be enough to achieve some parameters, and then these parameters just not changing that much. So the dependence on the number of iterations here is not very pronounced, but for the gradient-based algorithm, the effect was more kind of pronounced. So yeah, I do track. Okay, so and yeah, again, the clustered setting even more. It's in a way very artificial setup, of course. Here, what I'm doing, I'm clustering local data sets themselves. For example, this group of clients will have access only to digits 0, 1, and 2. This set of clients will only have samples from digits 3, 4, and 5, and this only like 6, 7, and 8. So we have a clustered setting, and what we're trying to learn is not 10 components, 10 digits, but 3. Again, if you think about it, trying to fit the centralized solutions here doesn't make any sense, because you are trying to learn 3 components which are very different for each cluster, right? And these scatter plots just show, like, for example, these nodes from one cluster. And again, within the cluster, we have very uneven split when it comes to the different digits. This is another cluster, and this is like a third cluster. When you look at the log likelihood, we can see, although the centralized training gives us quite nice the highest log likelihood, these clustering assignments are not exactly correct. And this is one kind of a confusing thing about the EM-based algorithms, that what we are optimizing is log likelihood loss, right? But sometimes we are not necessarily interested in the values of log likelihood. Sometimes we're interested in recovering, for example, true parameters of the data generative process, or like a true cluster assignments. And because the performance depends on separability of the Gaussians, or a variance, covariance, these two metrics are not always kind of linearly dependent on each other. So we can have high log likelihood, but somewhat low this NMI value, or like if you're measuring the squared Euclidean distance between the true parameters and like estimated parameters, then you can get not so optimal results. But we can see that our algorithm gives quite nice NMI values. And again, this advantage is diminishes once we are going to the more kind of equivalent split between the nodes, when this heterogeneity is diminishing. So when the nodes are similar to each other, it performs in a similar way as the local training, but better than centralized. And again, there is something weird happening with this gradient-based EM. But again, this algorithm has a bunch of hyperparameters, and maybe I just need to try to optimize it specifically for this data set. Okay, I'm done, I think, on time. So thank you for listening, and I'm very sorry that I exposed you to these very ugly plots, but I didn't find any other way to deliver this information without showing this. So if you're aware of any other way to visualize this type of numerical experiments or deliver these results, please let me know.